All right, so this is kind of a little bit of the backstory of trigonometry and how it was developed. So take a look at the triangle that's kind of put inside of this circle here. And imagine this triangle, you can visualize it here, it has a gray hypotenuse. Okay, the green side is going to be the leg opposite of my featured angle theta. And then the blue side is going to be the leg adjacent to my angle theta. Well, look how that relationship changes as theta gets smaller and larger. Look at how the green opposite side, if your featured angle is very small, the green opposite leg is going to be really tiny. And then as it gets larger, that green opposite leg gets enormous. Well, what trigonometry is over the years, mathematicians have started to um, we're able to compile these tables of the ratio or the relationship between a triangle's opposite green leg and its gray hypotenuse. And here's what they decided. So like at 30 degrees, at 30 degrees, this green leg is always 50% as long as the gray hypotenuse. And mathematicians have kind of known this relationship for thousands of years. Okay, but it doesn't end there. You can kind of continue, what happens at 45 degrees. At 45 degrees, the green opposite leg is about 70.7% as long as the gray hypotenuse. And you can find this for all these kind of major angles. At 75 degrees, the green opposite leg is about almost 97% as long as the gray hypotenuse. Okay? And so sine is just a collection of all of these percentages. How long is this green opposite leg as a percentage of the gray hypotenuse as we make the angle larger or as we make the angle shorter? Now, back in the day, all these relationships used to be put into tables like this, okay? Where at a 6-degree angle, if our featured angle is a 6-degree angle, then the opposite leg is going to be about 1% as long as the gray hypotenuse. And over the years, mathematicians started developing these tables that featured, not just your major like 15-degree angles and 30-degree angles, but using different calculations, they are able to find it all the way down to the nearest degree. What the length of the opposite leg is going to be as a percentage of the hypotenuse. And I want you to keep in mind, this percentage is going to hold true whether you have a really small triangle like what's on the screen, or if I were to, zoom in and make it a much larger, if I were to zoom in and make it a much larger triangle, well, the side lengths are going to change, but the percentage or the ratio is always going to be the same, whether it's a large triangle or whether it's a small triangle. The percentage isn't going to change. And so that's what a sine table is. The cosine table, very similar, although the cosine table is looking at this blue adjacent leg. And it's kind of the opposite of sine because look, if your angle is really small, this blue adjacent leg is going to be really large. And as here with cosine, as the angle gets larger, this blue adjacent leg gets smaller and smaller. And that's why cosine and sine are kind of the opposites. Sine is really tiny at a small angle, whereas cosine is really large at a small angle. Now as you go all the way up to like 90 degrees, this only goes to 45 degrees, but you get the idea. Sine and cosine are kind of opposites of each other in that regard. Now tangent then is this ratio of the green leg divided by the blue leg. So tangent's going to be really small with a small angle. But then you can see how as the green leg starts becoming larger than the blue leg, eventually it's going to become larger. Now here at 45 degree angles, the green leg and the blue leg are equal. So the tangent of 45 degrees, let me show you here, is equal to 1. If you can see that on the top of the screen right here, it's equal to 1. Now another interesting fact, sine and cosine can never get larger than 100%, and here's why. Remember that a leg can never be larger than the hypotenuse. So this green opposite leg is never going to become longer than the gray hypotenuse. The most it can ever come to equal is at 90 degrees, the green leg would be the same as the hypotenuse. That would be a ratio of 100%. And so the sine of 90 degrees is 1. but the green leg can never get larger than the hypotenuse, so it's never going to get larger than 1. And even if I kind of continue over here into this next quadrant, notice the green leg starts to shrink again. And this is why, even as I go all the way around this circle, which we'll come to know as the unit circle, even as I go all the way around this circle, the green leg will never become larger than the gray hypotenuse. And that's why this sine value will never become larger than 1. It will equal 1. It will equal 100% at 90 degrees, but it will never become larger than 1. That green leg, it will never be able to become longer than the gray hypotenuse. Okay? All right, so that is just a little introduction. And also a quick note on the calculator. If you don't have a scientific calculator, feel free to use Google Calculator. Make sure you're in degree mode. So if we had to do like, let's clear this out. If we had to do like 10 times the sine of 30, here's how we would enter this on the Google Calculator. And hold up. Oh, I'm in radian mode, sorry. Try that again in degree mode. There we go. So make sure this degree is highlighted. That's how we would type it in. And then to do inverse sine, I'd actually hit this inverse button. And here's how I get my inverse sines. If I had to do like inverse sine of some fraction like 52 divided by 60, something like that. Whoops. Try that again. Inverse sine, it shows up on your calculator as arc sine is how Google Calculator shows it, but this is the same as inverse sine. So if I had to do inverse sine of like 50 divided by 60, this is what it's going to look like on Google Calculator. Okay, that would be a 56-degree angle roughly. All right, so I hope that's helpful. Best of luck on this assignment. Bye.